All right, welcome everyone. Today, we're going to dive into something that's really at the very heart of computer science: computational thinking. The goal here is to learn how to think like a computer scientist, which is just a structured, powerful way to solve really complex problems, whether you're writing code or not. So, picture this. You're dropped into a busy hospital. It is absolute chaos. Lives are on the line, and you have this tangled mess of doctors, patients, equipment, and schedules. It feels completely overwhelming, right? Where would you even start? Well, this is exactly the kind of mess that computational thinking is designed to fix. Okay, so here's our roadmap for this lesson. First, we're going to learn how to properly define a problem to turn that chaos into clarity. Then we'll open up the computer scientist toolkit and look at 4 core concepts. After that, we'll see these ideas in action out in the real world. And finally, we'll talk about why this way of thinking is just so incredibly valuable for everyone. Okay, let's get right into it. Before you can even think about writing a single line of code, before you design any solution, you have to do the single most critical job of all. You have to understand and define the problem with perfect clarity. We've got to turn that vague mess into a precise map. And that brings us to our first key term, and it is a big one: problem specification. Now, you've got to understand, this is not just a casual description. It is a formal, precise blueprint that outlines every single essential part of the problem. It details everything: who's involved, what the limits are, what the goals are. Without a solid problem specification, any solution you come up with is basically just a shot in the dark. So how do you actually build this blueprint? Well, a really good problem spec has 6 essential parts. You start with a clear problem statement. What is it exactly that we're trying to solve? Then you define the constraints, things like budget or time or technology limits. Your objectives are the outcomes you want. Input and output specs are all about the data, what goes in and what comes out. And finally, the evaluation criteria. That's how you'll know if you've actually succeeded. And this slide just perfectly shows the difference. On the left, you have this totally useless statement: our customer service is inefficient. What does that even mean? It's vague. But now look at the right. This is what we're talking about. It's powerful because it's specific and it's measurable. A 25-minute wait time, a 15% jump in abandoned calls. Now we have concrete, quantifiable targets we can actually work with. Before you go any further, you absolutely have to know who you're building this for. And that brings us to another super important term: stakeholder. A stakeholder is basically anyone, any person, any group who is affected by the project. These are the real people, your users, your clients, your team. Their needs are the whole reason you're doing this in the first place. Let's make this real. Let's go back to that hospital idea. Who are the stakeholders? Well, you've got the doctors and nurses on the front lines, and they need something that's fast and easy to use. Then you have the patients. Their care, maybe even their lives, depend on this system working correctly. You've also got technicians who need to track expensive equipment, and of course the hospital administrators, who are probably worried about efficiency and costs. Each of these groups has totally different needs, and sometimes those needs even conflict. You have to consider all of them. All right, so once we have that crystal clear problem specification, it is time to open up the toolkit. We're going to look at the 4 fundamental concepts of computational thinking that you can pretty much apply to any problem you'll ever face. First up, we've got decomposition. This is basically the art of taking a huge, terrifying problem and just chopping it up into smaller, bite-sized pieces that you can actually handle. And here's a really common mistake to avoid. At this stage, you're breaking down the problem, not a computer program that doesn't even exist yet. We are still planning. I mean, think about your smartphone. As a single object, it is insanely complex, right? But if you decompose the problem of building one, it becomes a set of smaller problems. Design the screen, engineer the battery, write the operating system, and so on. Each of those is a much more focused, solvable task. It turns this impossible challenge into a checklist you can actually work through. Now, once you have those smaller pieces, that leads us naturally to our next tool: pattern recognition. This is all about being a detective. You're looking for similarities, for trends, for things that repeat. Because once you spot a pattern, you can often just reuse a solution that's worked before. It's about working smarter, not harder. Here's a super simple example. You look at this and your brain instantly sees the pattern, right? It's add 2. And because you recognize that pattern, you don't just know that the next number is 10, you can figure out the millionth number in the sequence if you had to. That is the power of finding the underlying rule.
Okay, our third tool is abstraction. And honestly, this might be the most powerful one. It's the skill of filtering out all the junk, all the noise, and focusing only on what is absolutely essential. You're basically creating a simplified model of reality so you can think about it more clearly. You're deliberately ignoring the details that don't matter.
The London Tube map is probably the most famous example of this in the world. Look, that map is a total lie, geographically speaking. It doesn't show the real twists and turns of the tunnels or the actual distances. But that's what makes it brilliant. It abstracts away all that useless detail to show you only what you need to know, how to get from one station to the next. It's useful because it's simple. Let's try another one. Say you're building a model to predict the outcome of a football match. What details matter? The color of the player's shoelaces? Nope, that's noise. What about a star player's recent injury, or the team's win-loss record against this specific opponent? Absolutely, that is the essential information. Abstraction is just knowing what to focus on and what to ignore. And that brings us to the final tool in our kit, algorithmic design. So, you've broken the problem down, you've found your patterns, you've stripped away the noise. Now what? Well, now you need a plan. And an algorithm is exactly that. It is a precise, step-by-step recipe of instructions that, if you follow it perfectly, will solve your problem every single time. Check out this super simple algorithm. Every single step is perfectly clear. It's unambiguous. There's no guesswork, right? A person could follow this, a computer could follow this, and it will always work. It is a foolproof plan for this one specific task. This is the blueprint for your final solution. So, we've defined our problem, and we've got our 4 core tools. Now let's see how this all comes together in some of the most advanced fields out there today. This table is awesome because it shows that these concepts don't live in isolation. They all work together. Let's take machine learning, for instance. You decompose a project into stages, like collecting data and training the model. The model then learns by recognizing patterns in that data, like features in an image that tell it, this is a cat. And it all works because of abstraction, where a complex, real-world cat is simplified into just a set of digital features and a label. The same thing happens in data analysis, in network security. It's the same toolkit everywhere. So, we've covered a ton of ground here. But let's get to the big question. Why does any of this matter? Especially if you're not planning on becoming a programmer. And this is the big takeaway, the most important thing I want you to remember. Computational thinking is not about thinking like a computer. It's about learning to think like a problem solver. It gives you a structured, repeatable, and incredibly powerful framework to tackle any complex challenge that life throws at you, whether that's in business or science or even just planning a trip. And that brings us to one last thing to chew on. We've seen that pattern recognition is a huge part of this, and it's something that machines are getting unbelievably good at. So I'll leave you with this question to ponder. If a machine can learn from patterns and make predictions with incredible accuracy, can it ever truly know something the way a person does? What does knowledge even mean when it exists outside of a human mind? Something to think about. Thanks for tuning in.